Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled Week 1 Review. Okay guys, so we have gone over a monton of stuff this week. And if you have survived the shelling I have given you, you should be able to knock out this Week 1 review with no problem. Perhaps you may want to review certain portions of the lectures, but to me, if you get through this Week 1 review, understanding what I'm going over here, you are pretty on the track. I understand there might be a couple of things that you're not sure of yet, but just review some of those lectures. You might be able to pick up what we're missing. This is kind of just a self-test here. We've got a couple of tasks here. We're going to do them in sequential order. Go ahead and pause these lectures as I get to the point and explain what the tasks are. Do work on it yourself, see if you come up with the same thing. Waveform A. It's got a frequency of 5 kilohertz. It's got a duty cycle of 25%. I want you to set up the function generator to produce this waveform. I'm asking you, give me what the voltage peak to peak, give me what the period is, give me what the pulse width, i.e. the on time is, if you should put in a DC offset in it. And once you're done with that, I want you to show what that same waveform would look like on an oscilloscope on channel 1 with the following settings. And use this big old oscilloscope, simulated oscilloscope screen over here on the right, when the vertical sensitivity is 2 volts per division and the horizontal sensitivity is 50 microseconds per division. Pause the recording at this time, go ahead and work these things out, see if you come up with the answers that I'm about to give you right now. What is the desired waveform, TTL compatible waveform look like? It goes from 0 to 5 volts. So our answer for voltage peak to peak is 5 volts. However, you have to realize the square wave is zero centered. So that goes from plus 2.5 down to negative 2.5. So what is the DC offset I want to put? 2.5 volts. What is the period for a 5 kilohertz waveform? T1 over F. 1 over 5,000 is 200 microseconds. When there's something that has a duty cycle of 25%, it's on a quarter of the time, that pulse width should be 50 microseconds. Figure out what it's going to look like. Use your oscilloscope. The settings are 50 microseconds per division. So there's 50, 100, 150, 200. That's my period. So every 4 blocks, it's going to repeat itself. If it's got a 25% duty cycle, it's going to be on for 50, off for 150, on for 50, off for 150, on for 50, so on and so forth. It's going to repeat itself. Vertical sensitivity, 2 volts per division. If I'm going from 0 volts, oops, what happened there? If I go in from 0 volts, I'm assuming that is where I've placed channel 1, 0. If that's 0 volts, that's 2 volts, that's 4 volts, that's 6 volts. Where does 5 volts? Right there. So my final waveform should look something like this. I'm drawing it in yellow, so I've got red everywhere. That is a 5 kilohertz waveform with a 25% duty cycle displayed on an oscilloscope with 2 volts per division, 50 microseconds per division. Okay, task 2. Apply that same waveform to the input of a NOT gate. Show waveform NOT A. I don't know if you can see that right there. NOT A on oscilloscope channel 2 with the same settings as channel 1. What are you going to get? Well, chances are you're going to get nothing, because check it out. You forgot to provide power to the 7404 VCC pin. 5 volts DC and ground. Just kidding. You probably did, because I've been harping on you so much. I put that yellow signal on pin 1. I get out a signal on channel 2, which is the exact opposite of pin 1. Okay, the one on pin 1. What's that look like? A mess, because it's right on top of that one. How can I get channel 2 away? I adjust its 0 center down so I can simultaneously display those waveforms. What does it look like? The mirror image of it. And if I zoom in, again, remember I was talking about those glitches there, I go ahead and adjust my my horizontal sensitivity. I might even be able to see some of those glitch states right there where there is a little bit of a transitional delay. How'd you do? How'd you do on task 1 and task 2? If you're tracking, you should have been able to accomplish those pretty easily using some of the skills we have already in our bag of tricks from our basic electronics, some of the very basic stuff I've taught you in digital electronics. Let's go on to some further examples here. I've just given you some very basic schematics. Let's assume that you're following proper wiring procedures and everything is got its +5s and 0s. So here is task 3's, the first one of task 3. Given the below oscilloscope screenshots, determine the expected value for the missing waveform on channel 3. Channel 1 is being provided to one input of an AND gate. Channel 2 is being provided to the other input of an AND gate. What does channel 3 look like? Go ahead, pause it. And what you should be getting, channel 3, if you got it set up correctly, should look like that. What is the truth table for an AND gate? Don't even worry about the truth table. Describe it. Its output is high when both inputs are high, or when all inputs are high. What is the only time in our timing diagram when both inputs are high or all inputs are high? Right there. Let's move on to the second one in task 3. Here we've got an OR gate. Channel 1 in red is on one input. Channel 2 in blue is on the other. What does the output of channel 3 look like? Okay, go ahead and pause it, work it out. Okay, channel 3's output should look like this. Channel 3's output is high when any input is high. A is high, B is high, A is high. Or channel 1 is high, channel 2 is high, channel 1 is high. All that time. It's an OR gate. It'll give you a high output. So what I'm just doing here is just, I know it's a simple, stupid exercise. It seems like I'm doing some of those same timing diagram exercises over and over. I'm just applying to the oscilloscope because this is what you're going to do in lab. You need to know the expected values to see if your circuit's working correctly. That's the basis of troubleshooting. Know how it works to begin with. And people think that troubleshooting is this external skill to knowing how things work. It's not. You need to know how things work. Let's go into some troubleshooting perhaps now. I've got channel 1. I've got channel 2, but look where the oscilloscope, again, stay organized. Stay organized. Where is channel 2? Channel 2 is the output. Channel 1 is a known input. What might you expect the input for channel 3 to be? Okay, this is hard. This takes a little bit of thought. So pause and think about this. What could the output of channel 3 look like? And there are a number of right answers. So, okay, you're back. Hopefully you've come up with something like this. From this region, if this is the output, from this region back, I don't know what channel 3 looks like. Could be high, it could be low. From this region on, I guarantee you channel 3 has a brief pulse there, and then it's a 0. From this region on, it could be a 1, or it could be a 0. I don't know. This region on, it's 0. Same thing that's occurring here. How can I make these bold assumptions here? Well, if channel 1 is an input and channel 2 is the output, channel 2 is having a high pulse there. Okay, if channel 1 is not providing that pulse, who is? Channel 3. What about these unknown regions? Well, check this out. What if I had a waveform that looked like this? The output would still be the same as channel 2 because channel 1 is providing that larger pulse. So we don't know what's in here. What you'll often see on the simulators is kind of this hashed out 1 and 0. Don't worry about it. You're not going to see that in the oscilloscope. But what I'm saying is this is a great reverse detective game. Okay, knowing one input and the output, what could the other input be? So these are great detective games. That was a little bit harder. Finally, this guy. Harder still, because there's some oscilloscope interpretation problems you might have to deal with here. Channel 1 is an input. Channel 2 is an output. We don't know what channel 3 is, because we don't have a channel 3. We don't know what the other input is. First off, what's the output for channel 2? Have I zero centered it here? Then my output is 0. Have I zero centered it here? Then my output is a 1. Have I zero centered it here and accidentally inverted the output? There are all sorts of problems that you could have with an oscilloscope if you're not setting the equipment up correctly. Let's pretend there's our zero center. My output is always 1. What's the problem here? What's the problem? What is the input? What's the input there? A ORed with question mark always produces a 1. What is the thing in the question mark? Go back to what we learned in the OR lectures. Anything ORed with 1 is always a 1. So it helps to, if you're getting erroneous data, let's pretend that is you don't want it to be a constant high. You might have inadvertently shorted this thing to plus 5 volts. Obviously, that OR gate is constantly going to produce a 1 output. Start predicting these things. If you see weird data, okay, hey, something's going on here. What could be the potential problems? Look back. If you've got the erroneous output, you might be giving an erroneous input. Okay, so now here is the hardest problem in our task, in our little review here. And again, some of this stuff, it may be a little above you right now, but you're gonna work this out in lab. What if my zero center really is there? I have an output of 0 for an OR gate that has data coming into channel 1. I don't know what's in channel 2. Is channel 2 the problem? No, because there's nothing. Anytime that there's A or 0, it's always A or 1, it's always 1. There's never an identity that we've learned thus far where it's a 0 on that side. There's something wrong. There's one of two places. There's two things that I'm going to go over. There's a whole bunch of ways to mess things up. There are two things that could possibly be wrong. Number one, you may have shorted channel 2 to ground. No duh, it's ground. You might not even have channel 2 hooked up. Your oscilloscope might be over here, hooked on some other pin. Common problem. Some other pin on some other chip and some other proto board and some other lab in some other state. They were just so close to each other that you hooked them up. It happens. You got 16 pins in some of these things. You're going to grab the wrong pin. The other thing is channel 1. Are you even sending channel 1 to there? Okay, it might have no input data on there. You might have shorted channel 1 to ground and the other input to ground. Obviously, 0 or 0 is ground. 0 or 0 is 0. And you might be grabbing your oscilloscope from this end. So it helps to recognize these totally erroneous states. So I know I promised a review, but I gave you two pretty challenging exercises at the very end. You should have at least been able to knock out task 1 and 2 and the first 2 from task 3. Some of these other ones are a little bit more complicated, which you get to do in lab.